Hi, my name is Mugisha, and today we'll be looking at the behavior of artificial satellites that orbit around the Earth. Firstly, we'll look at the Hubble Space Telescope. Its primary purpose included high-resolution imaging of distant galaxies, nebula, planets, and other cosmic phenomena free from atmospheric interference. NASA partnered with the European Space Agency, which uh, contributed solar arrays and instruments in exchange for 15% of the telescope time. This was done to combat one of the challenges they faced, which was Project Cuts of 1970s, and which had seen them reduce the mirror size and limit instrumentation. It was initially launched on 28th January 1983, but due to the Space Shuttle Challenger disaster, which saw the spacecraft break apart 73 seconds into flight, killing 7 crew members as seen uh, on the PowerPoint. The Hubble Space Telescope was finally launched on 24th April 1990 aboard the Space Shuttle Discovery STS-31 from Kennedy Space Center, Florida, USA. It was It has a low Earth orbit with an altitude of approximately 483 kilometers. Uh, it had an operation lifetime of 15 years, but this was later extended through servicing missions. We can also calculate the orbital velocity of the Hubble Space Telescope using this formula as seen on the screen. The radius we use is the radius of the Earth plus the altitude at which it sits. And as we can see, the velocity is 7.63 times 10 power 3 meters per second. And since, as also observed on the screen, that it has an eccentricity of approximately 0, with some sources putting it at 0.000021 and others putting it at 0.002107, we can see that it maintains this velocity throughout its orbiting of the Earth. We will also look at the Eutelsat 172B. This is a French communication satellite built by Airbus Defence and Space. It was launched from Guinea Space Center in French Guinea, South America on June 1st, 2017 aboard the Ariane 5 ECA rocket. It was launched into the geosynchronous orbit initially, and an electric propulsion was used to propel it into the geostationary orbit over a period of 4 months. This was more efficient than the standard chemical propulsion and means the satellite is expected to have a lifespan of more than 15 years due to the conservation of power. It has an altitude of 35,789 kilometers. What is its importance? It provides video broadcasting and broadband internet in remote areas. The satellite is used for news gathering and government institutional comms. Some of the challenges it faces is the limited fuel to sustain the orbital movement, meaning that at some point it will probably be decommissioned because it will move outside of its orbit. There's also the congestion in the GEO, which is the geostationary orbit, because of all the signals from all the different satellites, and also the difficulty in signal propagation due to the distance. Some of its orbital behaviors, as can be observed, is that we can calculate the velocity of this orbit, and we find that it's 3.07 times 10 power 3, and because it has an eccentricity of which is also approximately 0, it maintains this velocity. It experiences a centripetal force of 7.8 times 10 power 2 newtons. It also has a period of 24 hours, as we are aware of geostationary satellites moving in the same period as the Earth's revolution. We'll then move to the Molniya 1 satellite, which was launched on 23rd April 1965 in Baikonur Cosmodrome in northern Russia. It is a communication satellite, and it has an altitude of, ranging from 500 kilometers to approximately 400 approximately 40,000 kilometers. This difference in altitude is due to its high inclination and eccentricity of the orbit. This is a specialized orbit called this is a specialized orbit called a Molniya orbit. It was designed to be highly elliptical so that the satellite can spend more time over the high altitude region. It ends up spending up to 8 hours above the northern hemisphere. This is because of Kepler's second law that says that the satellites move fastest near the perigee and slowest near the apogee. So with the way it was designed, it will spend most of its time because it's moving slower in the northern hemisphere. It has a lifespan of 0.5 to 2 years, which is short relative to other satellites. This is mainly due to its elliptical orbit, which forces its perigee to pass through Earth's upper atmosphere, causing atmospheric drag that slowly decays the orbit. It has a period of 12 hours, which enables it to spend more time in the northern hemisphere for better communication connection. It has an eccentricity of 0.4, like we mentioned, which is high, which means it will have a different speed at different altitudes from the Earth. What is its importance? It was initially used for long distance radio communication in the Soviet Russia, which was USSR back then. It was used for telephone, telegraph, and fax across large distances. It enabled television broadcasting. Some of the challenges it has is that it launched in June 1964 and failed when the rocket booster lost thrust after 287 seconds. The second launch reached orbit, but the satellite failed because its antennas did not deploy. The PVC wrapped cables became brittle in low temperatures, cracked, and preventing the dishes from unfolding. The Molniya orbits require regular corrections because gravitational force and atmospheric drag alter the orbit, and without station keeping, the satellite's perigee drops until it eventually re-enters the atmosphere. The other thing is that the satellite hardware gradually degrades, especially the solar arrays and transponders, limiting each Molniya 1 satellite useful lifetime to about 1.5 to 2 years. Since this satellite is not moving in a perfect circle, we will calculate the instantaneous orbital velocity at the perigee and apogee. The perigee, of course, is the point where the satellite is closest to the Earth, and the apogee is the point when it is farthest from the Earth. First, we will look at the force it experiences at the perigee. It experiences a force of 9.12 times 10 power 4 newtons, and its velocity is approximately 7.56 times 10 power 3 meters per second. At the apogee, it experiences a centripetal force of 2.99 times 10 power 2 newtons, which makes sense because this is farther away from the Earth, meaning to experience a lower force, or a lower centripetal force. The velocity will also be lower, which is 2.93 times 10 power 3 meters per second. And then we'll look at escape velocity. Escape velocity is the minimum speed an object must have to escape a planet's gravitational field without further propulsion. A formula can be derived from equating kinetic energy to potential energy of objects in orbit. We'll use the Hubble Space Telescope as an example. So for the Hubble Space Telescope to switch its orbit from low Earth orbit to GEO, which is geostationary orbit, any changes will take place in both the kinetic and potential energy. Before I move to that, we can calculate the escape velocity, which we have done for the Hubble Space Telescope, which is approximately uh, uh, 1,737 meters per second, or 10.7 kilometers per second. This is the velocity needed to make potential energy zero. So the energy changes when a satellite is moving from high orbit to a low orbit. When the satellite is moving from a low orbit, to a high orbit, it means its potential energy will increase because it becomes a less negative, but its kinetic energy decreases. When it's moving from a high orbit to a low orbit, this means its potential energy decreases and its kinetic energy increases. We can look at these changes, kinetic energy change of the Hubble Space Telescope from low Earth orbit to GEO. The formula will begin with the formula for K equals a half mv squared, and we'll look at the velocity in the of this of the HST in the low Earth orbit, which is approximately 3.36 times 10 power 11 joules, and its new velocity that it will have at the GEO will be approximately 5.23 times 10 power times 10 power 10 joules. So as we can see that the change in kinetic energy will be the final minus the initial, which will be a negative 2.84 times 10 power 11. So you can see that the kinetic energy decreased. The potential energy when it's moving from low Earth orbit to GEO, we can calculate this, and we'll find that it's approximately negative 6.78 times 10 power 11 joules. And the new potential energy in the GEO will be approximately negative 1 times 10 power 11. And as you can see, that the change in potential energy will be positive 5.78 times 10 power 11. And then we'll also have to consider Hoffman's transfer. And we can use Hoffman's transfer to find the most energy efficient way of moving a satellite between two coplanar orbits, as we have been looking at satellites moving from one orbit to another. So for this to happen, two engine bands are required. The first increases the velocity at the lower orbit, which is the periapsis, to move into the elliptical transfer orbit that is tangential to both low and high orbits, while a second engine band adjusts the speed at the high orbit, which is called the apoapsis, to circularize it. First, we calculate the semi-major axis of the transfer orbit. This is the average of the radii of the departure and target orbits. As we can see here, we will use R1. R1 will be the radius of the Earth plus the altitude of the first orbit, and we'll find that it's 6.911 times 10 power 6 meters. This is the radius we're going to use of the Hubble Space Telescope when it's in the low Earth orbit. R2 will be got by also the radius of the Earth plus the new altitude of the GEO, which is the orbit you're trying to move our Hubble Space Telescope into. It will be approximately 4.2157 times 10 power 7 meters. And from there, we can easily calculate the semi-major axis. And we'll find that it's 2.4534 times 10 power 7 meters. After we have calculated this, we we can calculate the velocity of the perigee, which will be at R1, and the apogee, which will be at R2. This difference is because the transfer orbit is elliptical. So the velocity required at the apogee, which is the initial orbit, will be 9,954 meters per second. The second velocity required to circularize the elliptical transfer orbit and for the satellite to start moving in this new orbit will be got and it will be 1,638 meters per second. And so we have to consider the accuracy, reliability, and validity of the data that we have used and the different sources that we have cited as the sources we looked at to acquire this information. Most data and information was collected from respected scientific organizations like NASA, Union of Concerned Scientists, EO portal, and peer-reviewed academic literature. These sources have highly accurate information that is either gathered directly from spacecraft missions, official engineering documents, or scientific research. Their reputation as being factual also adds to their reliability. Websites like Heavens Above and InTheSky.org also supply accurate, up-to-date orbital data because they use real-time tracking information from NORAD, which, as you can see, is the North American Aerospace Defense Command. However, some sources like Wikipedia can contain accurate facts but are editable by the public, so their accuracy can vary. This makes them have very low reliability. Some sources used have moderate reliability, like history.com, which is a secondary source. Airbus press releases, which is reliable but may contain promotional bias. Overall, the sources are reliable because majority come from recognizable scientific institutions and provide accurate information. We will now consider the validity. The sources were valid because they gave technical information that included real-life data, historical context, and explanations for orbital types. Validity is, however, reduced by using old sources like USC 2014 that may not reflect more recent technology and general interest summaries like history.com provide summaries instead of technical documents. We can improve by using more peer-reviewed articles, reducing the dependency on Wikipedia, checking publication dates to have current information, but also including more international space agencies like ESA, JAXA, Roscosmos could provide technical detail for satellites like Molniya and Eutelsat, which are European-based telescopes. Thank you for listening. God bless.